Hello everyone, this is Mr. Smith. Thanks for coming back, glad to have you. We're going to continue our talk about the periodic table and how it is organized. This is a quick animation about what Mendeleev was seeing when he organized the video in the last video that we talked about. You have this pile of kind of cars that he was trying to make some sense of. And so what Mendeleev does is sort them by chemical and physical properties and similarities. So not only does he rank them by numbers of atomic mass, but he goes ahead and starts grouping them based off of some of the properties that he knows about. Things like conductivity, things like melting point and boiling point, and how does a certain chemical react with oxygen? How does it react with chlorine? Does it react with chlorine? Does it react with metals? Density, melting point, color. So there's quite a bit of information that can be known about the 63 or so elements that he has. And when he groups them, not only numerically in terms of increasing order, but starts putting them in columns if their properties are the same, you end up with something that looks a bit like the periodic table today. He wasn't kind of perfect, and he certainly wasn't complete of all 118 elements, but he was the one who gave us some sense. He kind of put the information that he had onto the table, so other people such as ourselves can take information from the table. So he put the information on the table, and we're going to take information off of the table. So what happens almost right away? What happens right away is we get these two kind of unequal halves. So this is a mostly complete periodic table. It doesn't include all 118 elements, only 112. Feel free to count those. But we have kind of two unequal halves of the periodic table. We have the metals and the nonmetals. The metals off to the left, the nonmetals off to the right. The nonmetals, I think there's 17 orange blocks there. Feel free to count that. So most of the 118 elements we have, only kind of a relatively small percentage of those are nonmetals. Everything else is metals. And notice they're all grouped together. And there's even a transition between metals and nonmetals. So Mendeleev piles all this information, or I guess knows all this information, organizes them, links these elements together, and it all turns out they have some similar properties, and they're grouped together based upon those properties. So what does a metal do versus a non-metal? So a metal we're quite familiar with in jewelry, in coinage, and wires, are really good at conducting electricity and heat. They're very shiny, which makes it good for electricity. Malleability means you can kind of stamp it, you can dent it, you can use sculptures for it. You can kind of hit it with a mallet and it will dent and bend. That's what malleability means. Ductility means that it can be made into a wire, which again we use for copper wires. In terms of valence electrons that Mendeleev wouldn't have known about, since he didn't know about electrons at all, let alone valence electrons. But typically speaking, as we can add more information onto the periodic table that he gave us, is that most of the metals have 1, 2, or 3 valence electrons, which are very loosely bound, which is going to matter for the chemical properties. Most of them are solids at room temperature, with one exception being mercury. So those are all the metal properties. Now the non-metal properties are going to be a bit of the opposite of that. The non-metals are not shiny, so we call that non-lustrous. They're poor conductors of heat and electricity. They're actually insulators. Instead of being malleable and ductile, they're actually brittle, which means they kind of fall apart. If you hit it with a hammer, it'll kind of crack apart into smaller bits of powder, which is not how metals work. Metals you can bend and twist and such. The non-metals are very brittle. And nonmetals can be solids. They could be gases, things like helium, neon, argon, krypton, radon, nitrogen gas, oxygen gas, chlorine gas, fluorine gas, hydrogen gas. I think I named all of the gases. There's still only one liquid, and that's liquid bromine, which is this picture here. And then there's quite a few solids: phosphorus, sulfur, carbon, and a few others. Notice they have more valence electrons, not 1, 2, or 3, but more like 6, 7, 8 valence electrons. And those electrons, instead of being loosely held, are very tightly bound. So again, we have kind of the polar opposites, non-metals versus metals. And they're all, clumped together on the periodic table. Now, of course, there's some middle ground, and we call those the metalloids. they have kind of properties that are kind of both. And we use those properties. One of the more important elements we have is silicon. In terms of Silicon Valley, that's the backbone of the computer boards. The silicon is not a conductor, which is what a nonmetal would do, but it has a very high melting point, which is something that a metal would do. And so we kind of make really good use of these metalloids for very specific uses. So here's the periodic table kind of broken up in another way. So this is kind of the whole complete thing. We have kind of two main groups. We call it kind of the group A and group B, also called the main group. The main group is only the first two columns and the last 6 columns. And then we don't call them anything other than not main groups. We call them transition metals. Is this 10 columns here in the middle? And then the inner transition metals are these 14 columns or 2 rows down here. Now we put these 2 rows down here because the periodic table will be kind of too long if we put these 14 columns where they're kind of supposed to be. So without this 14 blues, you'd have 18 columns, 2, 10, and 6. So you have 18 columns of, in this case, red, yellow, and green. So 18 columns can fit on a piece of paper. If you try to put 32 columns on the same piece of paper, you're almost doubling the width of the periodic table. So to keep that still printed on the same piece of paper, you'd have to shrink all the fonts in half. So for that kind of very practical reason, we put the inner transition metals down here off to the bottom. And so that's why they are there. And that's where kind of all these shapes come into play. So here we have the same periodic table, just kind of some more colors to it. Again, we have the main groups, which are numbered numbered in letters with A's. The not main groups are numbered with B's instead of A's. And then there's technically 18 columns of the periodic table, but when you're counting the main group, you count them 1, 2, 3, 4, 5, 6, 7, 8. If you're counting all of the columns, you count them 1 through 18. So here it is again, same periodic table, but now we actually have some more columns, more names that can be kind of applied to specific columns. The alkali metals in the first column, and I'll show this again, alkaline earth metals, the second column. The halogens are the second to last column, fluorine, chlorine, bromine, iodine. They are in the same group, they're in the same column. They are called a family because they're very similar. They do things chemically and physically in very similar ways. And that's the same truth for the alkali metals, which is the first column, not including hydrogen. Hydrogen is kind of in a family by itself. And the second column, from beryllium on down to radium, they do quite a few things in a very similar fashion. And so here you get another periodic table filled with colors, and kind of every element on the periodic table is in some kind of group. Again, alkaline metals, alkaline earth metals, transition, inner transition. Even the inner transition actually has different names for each row. And then you have your metalloids, your nonmetals, your halogens, your noble gases are a very important column. They have a filled shell of valence electrons, which makes them very stable. And so the periodic table is just flooded with information. You can Google quite a few periodic tables that give you all kinds of things. For this periodic table, it's actually color-coded based off the physical states. 273 is about 0 degrees Celsius. This unit is 273 Kelvin. So at 0 degrees Celsius, all the elements with black are solids. The blue ones are liquids, which again is mercury and bromine. The red elements are gases at room temperature, so there's hydrogen. And notice again, they're all off here to the side. Now, Mendeleev didn't know about the noble gases. He actually didn't believe they even existed. As smart as he was and as good as he was at filling in, or determining, discovering gaps like gallium and germanium, he actually didn't believe noble gases existed. But even still, they do exist. We've proven them to exist. Again, when we talked about the electron unit, we actually discovered helium in the sun before we discovered helium here on Earth. And being a very lightweight, colorless, odorless, unreactive gas, it makes it very difficult to detect in our own atmosphere. So there's a ton of information, and we're going to kind of go through it again in just a moment. All right, so here is a handout that we would have completed in class together. All of these things you can kind of look up online. So we used to have a web quest, but again, you have this information. So here's the information that we want you to know. The first column, and you can kind of see it's color coded with being alkali metals. The second column, alkaline earth metals. So kind of make sure your notes are good. Keep this kind of reference sheet handy for you, this note sheet handy for you. This green column over here are called the halogens, and the very last column over here is the noble gases. And again, the transition metals are in the middle, and then off to the bottom, and then my two shades of orange are both inner transition metals, but actually get different bits of vocab. The first column is named off the first row is named of the first element, which are the lanthanides and the actinides. So these first two elements here are lanthanum and actinium, and that names the whole rest of the row. Here is what I showed you at first, the metals and the nonmetals and the metalloids. Again, this is kind of the first and easiest one to kind of see just how many metals are on the periodic table. Most of the elements, about 80% of the elements, are metals, with about 17 or so are nonmetals, and about 7 or so are metalloids that have that transition between metals and nonmetals. We'll talk a little bit about that in the next lesson as to why there's a barrier, why there's a bit of a gray area. And then here are the main group elements. So these are the first two columns and the last 6 columns. These are the main groups. And then you have the pink and the green. You have the transition metals in pink and the inner transition metals in green. And so we have all this information, at least we have all these labels. What I want to do next is talk about what does an alkali metal mean? What does an alkaline earth metal mean? What are the properties that we associate with these families? So let me zoom in a bit. So here's the 4 main groups we're going to talk about. The alkali metals is in the first column of the periodic table. Only 1 valence electron makes them very reactive. Elements like to kind of, it's very easy for them to get rid of valence electrons. You kind of go for having 0 valence electrons or having 8 valence electrons. We call that something called the octet rule. So alkali metals are very easy to react to. These are the most reactive of all the metals. We'll talk more about that in the next video. When you add these to water, they release a lot of gas. They release a lot of fire as well. We should definitely track down those demos between sometime this unit and talk about just how reactive these alkali metals are. But you won't have any problem finding a YouTube video of alkali metals reacting with water. And then the alkaline earth metals still very reactive. They don't spit out fire when they react with water. 2 valence electrons, very increasingly soluble with decrease in temperature. So solubility is going to be a trend for those. And again, very reactive with water. And I guess not just water, but things in general. I pinpoint water because water is kind of all around us. It's in the moisture, it's in the rain, obviously, but it's in the moisture and the air. So these aren't really air-stable chemicals. In fact, you really don't find pure alkali metals, pure alkaline earth metals. You don't find pure unreactive sodium, lithium, calcium, barium, potassium. These are all so reactive that they react with something else. So even the potassium in your banana, that's already reacted to make something else, potassium ion. The calcium in your bone has already reacted with something else to become calcium carbonate. And sodium in table salt has already reacted with the chlorine to become something else. And we'll talk about bonding, we'll talk about chemical reactions in a later unit. The last 2 things are the halogens. So, and the noble gases, the halogens are the second to last column. They're nonmetals. They have 7 valence electrons. They're so close to working their way up to 8 to satisfy that octet rule that they too are very reactive. So they take in 1 electron from a metal, or from other nonmetals. They can actually share electrons to become a bit more stable. But when they do form ionic bonds, they form negative ions, and you're used to seeing that -3 for nitrogen, -2 for oxygen, and then -1 for fluorine, -1 for chlorine, -1 for bromine, -1 for iodine. And then the last one, it's not much to say. The noble gases do not react very much. They octet rule. They have all their energy shells that are occupied or filled, and that makes them very unreactive. So thank you for your time. Good luck with the edge elastic. Again, we have a periodic table that's just filled with so much information, and I can open that up here for us. There's so much information built into these periodic tables. These charges are what we've used so far earlier in the year in our ionic bonding nomenclature unit. And now that we can just kind of keep piling on more and more information built into this periodic table. So thank you for your time, and please remember, chemistry is everywhere.